So now we're going to mention the other two parts of the Sylow theorem. So given a prime P, we're going to let Sylow P of G be the set of Sylow P subgroups, which we know is a non-empty set by the theorem we just proved in the last video. And we let n sub P of G be the size of this set. So it's the number of Sylow P subgroups. And so why would we be interested in such things? Well, it turns out you can learn a lot about a group by studying its Sylow P subgroups. In fact, you will learn after the next chapter that you can start to actually classify groups up to isomorphism using this technology. Like quite literally, you can say that there are exactly 5 groups of order 8 up to isomorphism. Here they are, although that's actually a bit harder because 8 is just 2 cubed. But you'll see that there's exactly 2 groups up to isomorphism of order p times q, where p and q are distinct primes. And then it gets a little harder as the sizes of the groups get bigger, but you start to see proofs for classification theorems for the number of groups up to isomorphism. And a lot of the arguments rely on going through the Sylow P subgroups. And what do I mean by that? Well, because constructing groups is sort of an existential theorem, but you start to use this structure given an arbitrary group of a given size to construct isomorphisms between your abstract group and one of the concrete ones you've discovered before. Because, that's what the type of theorem you have to prove. If you want to say that there are only 2 groups of order 4 up to isomorphism, that's a statement that requires, stating what those 2 groups are, and then given an arbitrary group G of order 4, explaining how to prove which of the 2 groups it's isomorphic to. So these types of statements have pretty involved proofs. Anyhow, let me actually state the second and third Sylow theorems. So we're going to let P be a Sylow P subgroup. And we're just going to let GQ be any P subgroup. That just means it's of prime power order for some prime power. Then Q is actually a subgroup of a conjugate of P. So this theorem is pretty strong structural theorem. It tells you that all the subgroups of prime power order are related in some way, in the sense that any subgroup of prime power order is going to be a subgroup of the maximum one up to conjugation. In particular, this tells you that every P and Q in the Sylow subgroup set are conjugate. So in other words, the Sylow subgroups form a conjugacy class, which is not entirely obvious. Right now it's just, I defined it as a set, but it turns out that not only is it a set, but it's actually a conjugacy class. And not only is it a conjugacy class, but every subgroup of order or prime power order must be a subgroup of one of your Sylow P subgroups. In other words, suppose P were 2, and suppose that the maximum P subgroup was, say, 1024. What this is saying is that you're not going to be able to find a maximum subgroup maximal subgroup of size 64. That if you find a subgroup of size 64, it must be a subgroup of another group of size 1024. I mean, that's worth emphasizing, because just because you found a group of size D and a group of size D prime and D divides D prime, that does not tell you that K is a subgroup of H, or that K is a subgroup of a conjugate of H in arbitrary groups for arbitrary divisors. That type of stuff is rare. But this theorem tells you that that type of result is true for prime powers. Finally, since we know this result about conjugation, you can immediately ask, well, what's the size of this? What's the number of Sylow subgroups? It turns out that it's congruent to 1, modulo p. While at the same time being the index in G of any normalizer of P. Where P is any Sylow P subgroup. This last fact tells you that if you write G as P to the n m, where P does not divide m, then this n sub P must divide m. So this gives you a lot of structure. It tells you that the number of Sylow P subgroups must be up to subtraction by 1 is a multiple of P, and yet at the same time is a divisor of M. And you'll see for small, when the size of your group consists of a small number of factors, this gives you a lot of control. So I'm not going to prove these two Sylow theorems in this video because it's going to take some work to do that, but we are going to start looking at some applications of the Sylow theorems instead to give some idea of why these two results are pretty powerful. So the book starts to study groups of order P times Q, where P and Q are primes, but they only get halfway through that result because to finish it you have to go to the next chapter. So for the sake of actually getting something complete and relying on something we already know, I'm going to simplify a little bit. We're going to look at groups of order 2 times P. And we're going to classify them up to isomorphism. So we have two different primes here. You have, and of course I'm assuming P is greater than 3. We see in this case that a Sylow 2 subgroup has order 2. I can spell the word order, apparently. And a Sylow P subgroup, so I'll use T for that, and P for the Sylow P subgroup. But more importantly, because of the fact that those are prime sizes, this actually tells you that these are both cyclic groups. So what did the third theorem tell us? Focusing on P, it says NP must be congruent to 1 mod P. It also has to divide 2, whatever it is. So let's see, NP is 1P plus 1, 2P plus 1, and so on. And yet it has to be a divisor of 2. The divisors of 2 are 1 and 2. We obviously see the only choice is NP is equal to 1. So there's only one Sylow subgroup of Sylow P subgroup in G. And it's cyclic. What else can we conclude about this group? Well, remember, this is also a conjugacy class. if you have a conjugacy class of size 1, conjugacy classes of subgroups of size 1, then in fact this tells you that this Sylow subgroup has to be normal in G. Why? Because if it was not, then there would exist a G, since that GPG inverse was not P. But that would tell you that the number of Sylow P subgroups had to be at least 2. So, already just looking at just the Sylow P subgroups, we found a normal subgroup in G, even though we know absolutely nothing about G, other than its size. And we know that that normal subgroup has size P, and it's a cyclic group. Well, now we switch gears and we look at n sub 2, the number of Sylow 2 subgroups. It has to be congruent to 1 mod 2, which means it just has to be an odd number. And it has to divide P. Well, P is an odd prime, and so we see that n sub 2 is either 1 or it is P. So here we have at least 2 choices, and we're going to have to consider them separately. Well, let's focus on this case first. In this case, this subgroup of order 2 is also normal. So this means that there exists a x in G such that x squared is the identity, and the cyclic group generated by x is normal. Well, then you just look at this example and we look at P, and we say it's generated by something called y, for instance. And then we just look at G modulo the centralizer in G, the cyclic group X. We know that that has to be isomorphic to a subgroup of the automorphism group of C2. So that's not using this P yet, but this is just one fact we know, that G acts on a subgroup by conjugation. In this case, because X is a normal subgroup, we can act by conjugation by the larger group G, and this gives rise to an automorphism, as we've been discussing in the section on automorphisms. And the kernel of this action is the centralizer. But the automorphism group of C mod 2 is the trivial group. And so this tells us that G is equal to the centralizer in G of X, which says that every element in G commutes with every element in X, which means in particular X and Y commute. So we see that our group in this case is abelian. Moreover, X times Y has order 2p. Why? Because properties of exponents, you have to square the x to get the identity, and you have to take y to the pth power to get the identity. So the smallest power to get both of them to be the identity is 2 times p. And that means that we have an element of order 2 times p, which is the size of our group. That means that our group is just the cyclic group of size 2p. So now we look at the case where we have p subgroups of Sylow 2 subgroups. So let's think about this before we prove the result. We've got 2p elements. We also know that we have a p cycle, and we now have p conjugacy classes of subgroups of order 2, which means that we have p elements of order 2. what classical group are we used to studying that has a p cycle and a bunch of elements of order 2? So half the elements, we see that half the elements are order 2, and the other half are grouped together on a cycle. Well, that ought to remind us of the dihedral group. So this looks like the same structure as the dihedral group. Let's try to prove it is the dihedral group. So let's point out that conjugation by x, or element, so we know there exists an element of order 2. So we have conjugation by x squared is the identity. This is an automorphism on our Sylow P subgroup. Of course, since x has order 2, x inverse is just x, so you're just multiplying x, y, x together. And so this is an automorphism, which means that it lives in the automorphism group of P, which is isomorphic to the cyclic group C mod P. And as discussed in the video on isomorphisms, it's known that the automorphism group of a cyclic group of order P is a cyclic group of order P minus 1. Also worth pointing out, phi of x squared is phi of x squared, which is the identity map. So we're looking for an automorphism of order 2 in this cyclic group. This cyclic group has even size, so it has an automorphism of order 2. In fact, technically there's 2 choices. I mean, if you're looking for order at most 2. You either pick the identity map or you pick a different one. Now, of course, clearly if you pick the identity map, then x, y, x inverse is just y, and you're actually fixing everything pointwise. But that's just saying x and y commute, which means we're back in the previous example. And in that case, you can prove the subgroup generated by x is normal, in which case there's only one Sylow subgroup. So we can't be in that case. So it must be the case that we're looking for an automorphism of order 2. Well, what is the automorphism of a cyclic group of order 2? Well, if you think about it, at least one of the possible choices is negation. An abelian group inversion is going to give you an automorphism of order 2. Always. And if you think carefully, you'll realize that there is only one element of order 2 in a cyclic group of even order. And so there's only one possible automorphism, and we found it. And so since there's only one choice, we see that we must have in our group G, x, y, x inverse is equal to y inverse. More accurately, x, y, x is equal to y inverse. Or xy is equal to y inverse x. And remember, we also know x squared is the identity, and y to the p is the identity. And if you take these 3 things together, you see that we have our presentation from the book for the dihedral group. And so just knowing that there are p Sylow 2 subgroups and one Sylow P subgroup, we managed to prove that our group actually is the dihedral group. And so we've now managed to prove that if G has order 2p, where p is an odd prime, then actually G is either cyclic or dihedral. And that's what I meant when I said that with the Sylow theorems you can prove these kind of classification results, determining groups all the way up to isomorphism.